let then n be the complex number defined as that n is n squared plus n plus 1 plus I for n is natural, means 0 and positive integers. AI, find argument of z0. So what is z0? It's just when n is 0, it's argument of a complex number which is 1 plus I. How to find the argument? Let's consider this complex number on the organ diagram. Real part, imaginary part, and a number 1 plus I looks like this. X coordinate, it's the real part is 1 and the imaginary part is also 1 because 1I, and this distance from the origin is called the modulus of a given complex number, and this angle theta is the required argument, and we can see that there is isosceles triangle, and it's clear that this angle is 45 degrees or pi over 4. So this argument is 45 degrees or pi over 4. Write down an expression for argument of zn in terms of n. So in general, since n is 0 or any positive integer, a given complex number is always in the first quadrant, and x coordinate is n squared plus n plus 1, and y coordinate is 1, and we need the angle theta, and we can see that we can consider a right angle triangle, and tangent theta is opposite over adjacent, it's 1 over n squared plus n plus 1, so theta it's just arctangent of 1 divided by n squared plus n plus 1. So argument of Zn, it's arctangent of 1 divided by n squared plus n plus 1. The next, let Wn be the product of Z0, Z1, and so on up to Zn. Again, n is 0 positive integers. Bi shows that arctangent of A plus arctangent of B is arctangent of a given expression. It's a very typical situation when you meet the sum of two arctangents. To simplify it, we use a formula from a data booklet, and we should consider tangent of the left hand side, which is tangent over the sum arctangent of A plus arctangent of B, and it is given a formula in a data booklet that tangent of A plus minus B, it's tangent A plus minus tangent B, 1 minus plus tangent A multiplied by tangent B. Should be correct. So it becomes tangent of arctangent of A plus tangent of arctangent of B divided by 1 minus tangent of arctangent of A multiplied by tangent of arctangent of B. Tangent of arctangent is just a value because tangent is the inverse function of tangent, so it becomes just A plus B divided by 1 minus A multiplied by b, and it's tangent of the right hand side, hence the left hand side is equal to the right hand side, and a given statement is true. The next hence otherwise shows that argument of W1 is arctangent of 2. What is W1? It's a product Z0 plus Z1. So let's consider W1. It's Z0 multiplied by Z1. Z0 it's when n is 0, it's just 1 plus I, and Z1 it's when n is 1, it becomes 1 plus 1 plus 1, it's 3 plus I. And the first way is just to simplify it. Let's expand it. It becomes 3 plus 3i plus I squared, which is -1, so it becomes what? 2 plus 4i, and it's the first quadrant again, and similarly argument of W1 is just arctangent of y over x. It's 4/2. It's arctangent of 2 as required. Another way is the next. If a complex number is the product of two complex numbers, argument is the sum of arguments. It becomes clear when we consider two complex numbers which are given in Euler's form. So it looks like this: r1 e to the power of I theta 1 multiplied by r2 e to the power of I theta 2, and we can see that it becomes r1 r2 e to the power of I theta 1 plus theta 2. So we can see that the resultant argument is the sum of arguments. So we can say the next, that argument of W1 it's argument of Z0 multiplied by argument of Z1, and argument of Z0 it's actually 45 degrees, or we can say that it's arctangent of 1 plus arctangent of what? 3 plus I, it's 1/3. And using this formula, it's arctangent of a plus b, it's 1 plus 1/3, 1 minus 1 multiplied by 1/3, and it's arctangent of 4/3 divided by 2/3. It's arctangent of 2 as required. The next, prove by mathematical induction that argument of Wn is arctangent of n plus 1 for n is natural, it means 0 or any positive integer. And we start as usual. We consider the smallest positive value of n, it's 0, so let's consider for n is 1. It becomes what? Argument of W0. Argument of W0 is just argument of Z0. It's pi over 4, 45 degrees, or arctangent of 1. It's arctangent of 1. And from the statement, it's from A, and from the statement where is statement, it's this one. We can see that it should be arctangent of n plus 1, so it's argument of w0 is arctangent of 0 plus 1 is arctangent of 1. Arctangent of 1, so true for n is 0. The next, we write assume true for n is k, and we write a given statement which is argument of wn, argument of wn, but since n is k, we write argument of wk is equal to arctangent of k plus 1. And the next step is we consider n is k plus 1, and we consider argument of wk plus 1, and its argument of z0, z1, and so on up to zk minus 1, zk, and zk plus 1. And we know that argument of the product is the sum of arguments, and we can write that it's argument of z0, z1, and so on up to zk minus 1, zk plus argument of zk plus 1, and this product is argument of wk plus argument of zk plus 1, and argument of wk we use this assume, and it's arctangent of k plus 1, so it's arctangent of k plus 1 plus what is argument of k plus 1? It's argument of only one value, one complex number, and it was the general form. Argument of zn, it's arctangent of 1 over n squared plus n plus 1, and we need to consider just n to be k plus 1. So substituting k plus 1 for n, we get that it becomes arctangent of 1 divided by k plus 1 squared plus k plus 1 plus 1. And we should simplify it, and we know that we must get finally that this sum of two arctangents is equal to arctangent of k plus 2, because in general it's arctangent of n plus 1, and we consider n to be equal to k plus 1, so we should get arctangent of k plus 2, and it's a hint actually, because we know what we must get finally. And it's clear that to simplify it, we should use the previous formula. Arctangent plus arctangent, it's what? It's arctangent of what? It's the sum k plus 1 over, let's simplify it, so it becomes k squared plus 2k plus k, so plus 3k plus 1 plus 1 plus 1, so plus 3 divided by 1 minus and product of k plus 1 and 1 over, so this k squared plus 3k plus 3. Just use this formula, arctangent A plus arctangent B. And we need to simplify it. So we can multiply each term by k squared plus 3k plus 3, and we get the next k plus 1 k squared plus 3k plus 3 plus 1 is divided by k squared plus 3k plus 3 minus, notice that k plus 1, and you can open parentheses here, so it's minus k minus 1. And it becomes arctangent, and let's expand it. So it becomes k cubed plus 3k squared plus 3k plus k squared plus 3k plus 3 plus 1, and divided by k squared plus 2k plus 2 is arctangent, and k cubed plus 4k squared plus 6k plus 4 divided by k squared plus 2k plus 2. And notice that we know what do we must get. We must get finally arctangent over k plus 2. So this must be k plus 2. And how to get k plus 2? Definitely, since there is a polynomial of degree of 3 in the numerator and polynomial of degree of 2 in the denominator, it should be some linear factor multiplied by polynomial of degree of 2. So and actually it must be k plus 2 multiplied by what? By k squared plus 2k plus 2, because it must cancel with the denominator, so that k plus 2 remains only. Notice that you don't need to find what is the root to divide polynomials, because you know the answer, and it's a hint actually. And we can just check if we expand it. So let's check it, k cubed, let's check k squared, so we can get k squared when 2 is multiplied by k squared, so 2k squared plus 2k squared, 4k squared, correct. Let's check k, so k 2k plus 4k, 6k, correct, and 2 times 2, correct. So we can see that when we expand this, it is equal to this. If it doesn't the same, it means that there is a mistake, because it must be true. And finally, it's arctangent of k plus 2 as required. So it's true for n is k plus 1, and let's again, it must be, since we consider n is k plus 1, it must be k plus 1 plus 1, so k plus 2. And a conclusion. If true for n is k, true for n is k plus 1. Since true for n is 0, true for any n is natural. And That's all for this question.